Hello friends, welcome to Bindu Dhadwal chemistry lessons. Our topic for today is alkali metals. This is the second video of alkali metals. We'll be discussing chemical properties and general characteristics of compounds of alkali metals. So alkali metals are highly reactive due to their large size and low ionization enthalpy, and their reactivity increases down the group because size increases and ionization enthalpy decreases down the group. Reactivity towards air: alkali metals tarnish in dry air due to formation of their oxides, which in turn react with moisture to form hydroxides. Lithium forms monooxide, sodium forms peroxide, and potassium and other elements like rubidium and cesium will form superoxides as well. The oxidation state of alkali metals in these oxides is +1, but lithium, it can react with air, with the nitrogen of air to form lithium nitride as well. Other alkali metals do not form nitrides. Because of their high reactivity towards air and water, alkali metals are normally kept in kerosene oil. Lithium is kept in paraffin bags because lithium is lighter and floats on kerosene oil. Reactivity towards water: the alkali metals react with water to form hydroxides and dihydrogen. So M is the alkali metal and it will form hydroxide. Lithium has the most negative standard enthalpy of formation values. Its reaction with water is less vigorous because of small size and high hydration enthalpy. Other alkali metals react explosively with water. Sodium and potassium catch fire when react with water. Alkali metals also react with proton donors such as alcohols, gaseous ammonia, and alkynes. Reactivity towards dihydrogen: the alkali metals react with dihydrogen at about 673 Kelvin to form respective ionic hydrides. Lithium will react at 1073 Kelvin. Alkali metal hydrides are ionic solids with high melting points. Reactivity towards halogens: the alkali metals readily react with halogens. That is a vigorous reaction to form ionic halides, but lithium halide is covalent because of high polarization capability of lithium ion. As we have done, a small sized positively charged ion can distort the electron cloud of the negatively charged anion towards itself, bringing covalent character to the bond. And lithium, being smaller in size, has high polarization capability. So lithium iodide is most covalent because according to Fajan's rule, the lithium cation can polarize very effectively, and iodide, being bigger in size, can be polarized very easily. Reducing nature: the alkali metals are strong reducing agents. Lithium is the most powerful reducing agent and sodium the least. The reducing capability depends upon these three reactions. The solid metal will first sublime into gaseous metal atom. This the enthalpy involved is called sublimation enthalpy. Then metal loses its electron to form metal ion in the gaseous state. The enthalpy involved is ionization enthalpy, and the positively charged metal ion that gets surrounded with water molecules, and the enthalpy released is called hydration enthalpy. So reducing power represents the overall change. So in case of lithium, even though because of small size and high ionization enthalpy, the first two reactions engage more energy, but the hydration enthalpy released more than compensates for this, and so lithium is the most powerful reducing agent. With the small size of its ion, lithium has the highest hydration enthalpy, which accounts for its high negative E0 value and its high reducing power. A very interesting use of alkali metals is they dissolve in liquid ammonia, giving deep blue solutions which are conducting in nature. This is because in ammonia, when the metal dissolves, the metal will give electrons. Both the metal ion and electron get surrounded by ammonia, forming solvated cation, ammoniated metal cation, and solvated ammoniated. The blue color of the solution is due to the ammoniated electron, which absorbs energy in the visible region of light and thus imparts blue color to the solution. The solutions are paramagnetic, and on standing slowly liberate hydrogen, resulting in the formation of amide. So overall reaction is metal ions plus electron plus ammonia will form metal amide and hydrogen. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Uses of lithium. Lithium is used in formation of alloys. For example, with lead, it forms white metal, which is used for making bearings for motor engines. With aluminium, its alloy is used to make aircraft parts. With magnesium, its alloy is used to make armor plates. It is also used in thermonuclear reactions and to make electrochemical cells. Sodium is used to make a sodium lead alloy, which is needed to make tetraethyl lead or tetramethyl lead, which were earlier used as anti-knocking additives to petrol. Nowadays, lead-free petrol is used. Nowadays, these substances have been replaced with some less polluting anti-knocking agents. Liquid sodium metal is used as coolant in fast breeder nuclear reactions. Use of potassium. Potassium has a vital role in biological systems. Its chloride is used as fertilizer. Potassium hydroxide is used in the manufacture of soft soap, and potassium hydroxide is also used as an excellent absorbent of carbon dioxide. Uses of cesium. Cesium is used in devising photoelectric cells. General characteristics of compounds of alkali metals. So oxides and hydroxides of alkali metals, on combustion in excess of air, lithium will form monooxide, sodium peroxide, and potassium, rubidium, and cesium form superoxides like potassium superoxide, rubidium superoxide, and cesium superoxides. The increasing stability of peroxide or superoxide as the size of metal ion increases is due to the stabilization of larger anions by larger cations. As we go down, the size of cation increases. Now they can stabilize large anions like peroxide or superoxide anion. These oxides are easily hydrolyzed by water to form hydroxides. Metal oxide, metal peroxide, and superoxide all dissolve in water, forming metal hydroxides. In case of peroxide, hydrogen peroxide is formed. In case of superoxide, hydrogen peroxide and oxygen are formed. The oxides and the peroxides are colorless when pure, but the superoxides are yellow or orange in color. The superoxides are also paramagnetic. Sodium peroxide is widely used as an oxidizing agent in inorganic chemistry. The hydroxides are all white crystalline solids, and these hydroxides are the strongest of all bases and dissolve freely in water with evolution of much heat on account of intense hydration. The basic strength increases on moving down the group. Lithium hydroxide is least basic and cesium hydroxide is most basic. The halides. The alkali metal halides are all high melting colorless crystalline solids. They can be prepared by the reaction of appropriate oxides, hydroxides, or carbonates with aqueous hydrohalic acids. Metal oxide plus hydrohalic acid forms metal halide plus water. Similarly, hydroxides also form metal halides and carbonates. All of these halides have high negative enthalpies of formation. The enthalpy change of formation for fluorides becomes less negative as we go down the group. The reverse is true for chlorides, bromides and iodides. The enthalpy of formation becomes more negative as we go down the group. For a given metal, the enthalpy change for formation is always becomes less negative from fluoride to iodide. The melting and boiling points always follow this trend. Fluorides have highest melting and boiling points, and it will decrease down the group. All these halides are soluble in water, but lithium fluoride is less soluble due to high lattice enthalpy. The solubility is depends on the balance between the lattice enthalpy and hydration enthalpy, and in case of lithium fluoride, lattice enthalpy is high, whereas in case of cesium iodide, which is also less soluble, hydration enthalpy is less. So in these two cases the solubility is less, otherwise they are soluble. Other halides of lithium are soluble in ethanol, acetone and ethyl acetate because lithium halides are covalent in nature. Lithium chloride is also soluble in pyridine. Lithium fluoride is ionic in nature. Sodium chloride, being ionic, is insoluble in organic solvents.